will be off by 0.834 inches. Okay, the next thing I want to talk about is something called the coefficient of determination. Remember when I showed you how to turn your correlation on your calculator? You got the R thing, and right underneath it was R squared, or maybe the other way around. That R squared is called the coefficient of determination, and it's related to your data and how much of something can be predicted based on what your explanatory variable is. So the square of the correlation, R squared, is called the coefficient of determination. It is the part of the variation in your y values, your response variables, that can be attributed to or accounted by the least squared regression equation on your x. So when you're making your prediction equation, anything that's varying based on what your x is called this R squared, this correlation coefficient, that percentage or fraction. And when you write down a statement saying that, you can use one of the two phrases as a general rule. These are the ones that we generally use in our class. You would say blank percent of the variation in whatever the y thing is, or your response, can be accounted for by the least squared regression line. Or you could say something like the least squared regression line accounts for blank percent of the variation in the whatever the y is. So in our case up above, that was the distance traveled in inches, I think, right? Distance in air. So let me show you how that works on our calculator, just as an example. Oh, I guess they already gave us that. So let's just look at on the calculator how it pops up. So I look at my calculator, and if I were to go stat, calc, for enter, down below you see the R squared, 0.99698. So to 3 decimal places, 0.997.
What are the lists again? I want to know just regularly.
It's always, everything always defaults to list 1 or list 1 and 2, depending on if you're doing 1 variable or 2 variable statistics. So down below here, the sentence that they're using, 0.997, if we were to interpret that, and we pick one of these two phrases, I could say something like 99.7% of the variation in the distance in air traveled can be accounted for by the least squares regression line. So on our next slide here, since we don't use computers, we should be a little bit familiar with these computer outputs. And just so you know what's going on, it's kind of hard to read up here, for me at least. On the AP exam, you're going to give some information, be given some information from a computer output, and you have to interpret it. And so you need to know how to find things very fast, like slope, y-intercept, r, s, r squared, that kind of stuff. So down below here, if we're looking, let's say we're looking for the slope. And if I'm looking for the slope, in this particular thing over here to the left, I think this one is the, tell me if I'm right, is this the slope right here? It's hard for me to read on the...
Yeah, it says it's a slope.
Slope, okay. And then they also wanted standard deviation. So that's S. And the standard deviation, I think, is right here. So you can just kind of look for the location in the output and what these phrases are. Some of them are pretty easy, like the one that says S. That's not such a big deal because we know S is the standard deviation. The y-intercept is, to me at least, a little bit weird. So the y-intercept is up here. They call it the constant. What else do we need? R squared I think was one of the other things they wanted, right? R squared. Here's our R squared, and actually they do a pretty good job in this mini-tab program where they say RSQ, which kind of makes sense. So out of all these, the one that was the most confusing to me was the slope, where it says NEA change. Because to me, NEA is National Education Association, of which I'm a part of, so that's kind of weird. On the other one, which they call JMP, this is another program. It was a free program for kids to use. The R squared, which was our orange stuff, was up here. And down below that is that S? Right? So S is right below it. Like skip one, it's right there. The root mean square error is what it's called. And then the intercept we knew from before was our y-intercept. So that's this one. And then the last one, the NEA change, was the same as our slope. So I just want you to be familiar with where these things are on a computer output. So an example below here, using these computer outputs, we're going to do a bunch of stuff with it. So let's see how well does the number, bless you, of beers a person drinks predict his or her blood alcohol level, which we're going to call from now on the BAC. 16 volunteers, so that would be your N, with an initial BAC of 0, meaning they had no alcohol in their blood, drank randomly assigned number of cans of beer. 30 minutes later, a police officer measured their blood alcohol content. Least squared regression was performed. That's like our stat calc 4. And a scatter plot with regression line was added. A residual plot was shown, and some computer output from the regression are shown down below. Okay, so first of all, as we look through our table, kind of knowing what does the word constant mean?
Y-intercept.
Y-intercept. What do you think this coefficient for beers means? Slope. Okay, so just know when you're seeing these things, some of these things you'll have to interpret later, and we'll come back to that, no big deal. So on the left is the regression line. On the right is the residual plot. Look at the residual plot. Do you see a pattern? No, so it looks like the line's a good model. So let's answer some questions. First of all, what's the equation of this least squared regression that describes the relationship between the beers and the blood alcohol content, and define your variables? So whenever you're talking about a prediction line, you're going to start off with y hat. Son of a highlighter. Sorry. Y hat equals, and our beers coefficient was whatever up there, so I'm going to go with 0.017964x, and then minus 0.012701. So they both came from the table, and you can color code them from up above if you want to show which one was the slope and which one was the y-intercept. We have to define our variables. We didn't do that yet. So what is x? What?
Beers.
Number of beers. How about our y?
BAC.
The BAC. Okay, so just define it. Tell the reader what you're doing. Okay, so in part B, what does the slope mean? Well, it means, what does the lope mean? The lope is a ski race over in Theodore Wirth. Lope, it is a race. Lope, it. Okay, whatever. For every additional beer consumed, the BAC increases by, I'm just going to go with 0.018. But it is the 0.017964 if you want to be accurate to 5 decimals or 6 decimals. Okay, so from our table on the previous slide.
And the correlation.
it tells you, it says r squared, which is the correlation, that's equal to 0.8. So really the only way to find your correlation is you take the square root of that. So I square root that stuff, and r would be to 3 decimal places, maybe 894?
Yep. Well, that's what I got.
All right, thank you. Yes, r squared adjective. What does this mean? This means that 80% of the variation in BAC, because that's your response variable or your y, can be
80% or 89.4%?
accounted for by the LSRL. So is the line a good model?
Let's check.
How would you know?
Doesn't that show the positive whatever thing?
I don't know. We just got done talking about 10 minutes ago. How do you know if the line's a good model? There's no pattern. Look at the residual plot. Is there a pattern?
No.
No. So you say a line is an appropriate model since the residual plot shows no obvious pattern. Okay, so one of the things that's really good is I think a lot of people, Peter, shut it, did a good job of using their interpretation line or their least squared regression line in order to find an answer, which is exactly what the readers are expecting you to do. So for most of you, you did this. Y hat is equal to, why is that clock there? Negative 0.0127 plus 0.017964, or if you use the 8, whatever, times 9. And you got 0.148976. And I think most people in here did that and did a really good job. Okay? The problem is, what is that number? That's a prediction. That's not the actual blood alcohol content. That's the prediction. Okay? So now you need to find it. How can you do that? They gave you the way to find it. Look back on the previous page. 9 beers. Or sorry, 9 beers is right here, yes? So 9 beers, this is my residual. Which means that my prediction was off. The actual number was 0.4, I don't know, 0.04, I can't tell what that looks like. What does that look like to you?
0.044.
0.44. Okay, so we're going to use Malia's number. So I'm going to have to add on 0.044 to that to get the actual BAC. So if somebody could add those two numbers together, please.
And then minus 0.0.
No. No. Nope. Don't do the standard deviation thing. Just find what it would be with the residual. 193? Okay, so 0.193 is the actual BAC.